Hello and welcome. In this video, we are going to extend the idea of the difference quotient, which is the slope of the secant line, to the idea of finding the slope of the tangent line and how that relates to the derivative, or how in fact that actually is the derivative. So as you probably remember, we talked about how we could have a curve such as a parabola. And a parabola doesn't have a constant rate of change like a line does. So if we wanted to talk about the rate of change, we could talk about the slope of a secant line. We could talk about taking the slope between 2 points on the parabola and thinking of that as a line. So the slope of that line would give us the slope between those 2 points on the curve. And since those 2 points are on the curve, that is what gives us the idea of the secant line. So a secant line is a line that connects 2 points on the same function. Its slope is used to approximate the slope of a function at a given point. So if I wanted to know approximately what the slope is at this point, I could pick another point close by on the function and find the slope between those 2 points. And we have talked about that as x and x plus h, meaning I'm going some small distance away along the function h. And that is where this came from. This came from our fancy slope, is what we called this, or our difference quotient helps us to find the slope between 2 points on a function, the slope of a secant line. So we could say that that is delta y over delta x, the change in y over the change in x, where we're talking about some finite amount of change. So this right here is just the difference quotient. So ultimately, if we wanted to find the slope at a particular point, we wouldn't want a secant line, we would want a tangent line, a line that only touches our curve at exactly that point, and we would want to know what the slope of the line is at exactly that point. And that point, or that line, would be a tangent line. So let's use the difference quotient here with the function that we are being given and a particular value on the function, and let's just find the slope there. So we can say delta y over delta x, aka the slope, would be, if we apply the difference quotient, then I'm going to plug x plus h in here. So 2 times x plus h minus 3 minus f of x, which in this case is just 2x minus 3. And this whole thing is over h. And then we would go ahead and simplify. So we would distribute our 2x plus 2h minus 3, and then distribute that negative sign, minus 2x plus 3 over h. And then we would go ahead and simplify this. Well, 2x and negative 2x is 0, negative 3 and positive 3 is 0, so we would have 2h over h, which is just going to be 2. If there was a variable here, like an x, then we could plug in the c value that we're talking about, and we could say that 2 times x would give us 4, which would be the slope at that particular point. But we don't have an x, we just have a 2. So we're saying the slope of the tangent line is 2, which makes sense. That is the slope of this line, right? This function was originally the slope, and now we're saying we can use the difference quotient to find that slope using that particular value. Let's extend this idea a little bit further. So the difference quotient, in the difference quotient, the x plus h is talking about some finite amount of distance away from the original point x. But what would happen as we get closer and closer and closer together, or as that h value gets really small? What we're saying is that would make our points closer together, or we would get, hopefully, to the tangent point. And is there something in calculus that allows us to get closer and closer and closer to a particular value, or to h being 0 in this case, because that would make x plus h really just be the exact point that we're looking for on the function if h was 0. So the calculus idea that we have been using is the idea of a limit. So we could think about the limit as h is going to 0. So as h goes to 0, the secant line is getting very, very close to giving us the exact slope of the curve at a particular point. So we can use limits in order for us to be able to get really, really close. So the limit as h approaches 0 of that slope, or of the difference quotient, to get the exact value of the tangent line, or the slope of the tangent line. And the slope of the tangent line has a very specific name, and that is the derivative. So the derivative is the slope. You're going to hear me say this repeatedly because that's the one thing I hope you take away from this video. The derivative is the slope of the tangent line. So even though we're in calculus and talking about high-level concepts, we're really talking about an Algebra 1 level concept, the idea of slope. The derivative is the slope. Now, we have talked about how there are some functions where the slope is not constant, right? A line has a constant slope that is a number that is not changing. But if I think about a quadratic, the slope is negative over here, and then it's negative, but different negative. Then at some point it's 0. Then it starts turning around and becoming positive. So the slope is constantly changing as we move along the curve. So what would be really awesome is if we could have an equation or a function to describe the slope. So a derivative of a function is a function that describes the slope at a particular x value. So we could be given an equation. So if we want to know what the slope is in 2, we plug 2 into that derivative function and it tells us the slope there. If we wanted to know the slope at -4, we could plug -4 into that derivative function to find the slope of the tangent line to our original function at that particular x value. So we're going to talk about some notation here. All of these are different ways to write derivative. So this one right here reads f prime of x. This one is dy dx. This one here is d dx of f of x, meaning we're taking the derivative with respect to x of some function, f of x. And this one reads y prime. All of these are different notations that you're going to see when we're saying the derivative equals something. We're going to use one of these notations. And then down here is what we are currently going to use for the derivative. The derivative is the limit as h approaches 0 of the difference quotient. So this is the limit definition of a derivative. In future sections, we're going to define derivatives in different ways, or we're going to evaluate derivatives in different ways. But this idea is the derivative is the slope of the tangent line, and right now, the way that we know how to describe that is using the limit as h approaches 0 of the difference quotient. So let's go ahead and look at some practice problems using this limit definition of the derivative. Okay, here the directions say find the slope, meaning the derivative, find the slope of the tangent line to the given function at the given point c comma f of c. So let's just start with finding the derivative, meaning we are going to evaluate the difference quotient, but we're going to take the limit of the difference quotient as h approaches 0. So go ahead and pause the video and set that up on number 1. So we're saying f prime of x, meaning the derivative, is equal to the limit as h approaches 0 of what I get if I plug in x plus h, so x plus h quantity squared, plus 3 times x plus h minus my original function, x squared plus 3x, all over h. And now go ahead and simplify the difference quotient. Pause the video, simplify the difference quotient. So here I have expanded, and now I'm going to combine like terms. And then I notice that each of those terms that is left, I could divide an h out of. So now I'm here, and now I can evaluate the limit using Chapter 1 strategies. So I can substitute in 0 for h, which just makes h become 0. So this limit is going to equal 2x plus 3, since we were taking the limit as h approaches 0, not as x approaches 0. So this question asked us to evaluate this derivative when c, or when the x value, is 2. So let's go ahead and plug 2 in. So I'm going to say f prime of 2, meaning I'm plugging 2 in, is 2 times 2 plus 3, which is 7. So the slope, which is the derivative for this curve, x squared plus 3x, at x equals 2, or c equals 2, is 7. Let's look at another example. So we're going to set up our limit on number 2. F prime of x is going to equal the limit of the difference quotient. And then we're going to simplify. So here's the difference quotient set up. We can't directly substitute in 0 for h because we would get indeterminate form. What we can do, using those strategies we learned in Chapter 1, is we can multiply by the conjugate and see where that gets us. So now we're here. In the numerator, this negative x and this positive x are going to add to be 0, and this h is going to divide out. So we're going to have the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And now we can use direct substitution and plug in the fact that h is 0. That's going to give us 1 over the square root of x plus the square root of x, or 1 over 2 root x. But we know that we're going to plug a number in. We're going to plug in 3. So I'm going to rewrite that as 1 over 2 times the square root of x. In this case, what we're going to say is that f prime of 3 is equal to 1 over 2 times the square root of 3. So the slope of the tangent line to the function, the square root of x, f of x equals the square root of x, at x equals 3 is 1 over 2 root 3. That is our slope at that point. But if we just want the function and we want to leave it as a function, that could be helpful in case we want to find the derivative at more than one value. It would be great to just have a function to keep in mind when looking at the derivative. So let's look at how to do that. So let's talk about finding the derivative, not necessarily at a particular point, just finding the derivative as a function. We're basically going to work through the process we just worked through on the last two questions. We're going to apply the limit of the difference quotient for the given function. We're going to simplify, which means that we may need to use strategies from Chapter 1, factoring, conjugates, trig identities, things like that. We may need to, step 3, evaluate the limit as h approaches 0. Again, we're going to have to use those techniques from Chapter 1 and then express our final answer as y prime or f prime of x or dy dx, depending on how the original problem was written. So if we're originally given a function f, then we're going to have our final answer be f prime of x equals the function. So that's how it's going to look for this first one. So we're again going to start by saying f prime of x is going to equal the limit as h approaches 0 of 3 times x plus h minus 3x all over h. And then we're going to simplify. So I'm going to distribute in the numerator. And then I can simplify here. This is going to be 0. This is going to be the limit as h approaches 0 of 3h over h, which means those h's are going to divide out, and I'm just going to get 3. Well, that should make complete sense. This function is a line. The slope of that line is constant everywhere, and the slope of that line is 3. So let's extend this idea to functions that are maybe slightly more complicated. So we're going to take the limit as h approaches 0 of 4 times x plus h quantity squared minus 4x squared all over h. We're going to use binomial expansion to expand that numerator. So that's going to be 4x squared plus 8xh plus h squared minus 4x squared all over h. These are going to add to be 0. So we're going to have the limit as h approaches 0 of 8xh plus h squared over h. I can divide that h out, so the limit as h approaches 0 of 8x plus h, since I can divide this one out and one of those. And as h goes to 0, this limit is just going to be 8x. So f prime of x is going to equal 8x. So now if I wanted to find the derivative when x is 0, it would be 0. If I wanted to find the derivative when x is 2, it would be 8 times 2, or 16. So I now have a function in which I can find the derivative at any particular x value. So let's go ahead and work through number 4. And if you're feeling pretty confident in this process, I encourage you to pause the video and try it on your own. Otherwise, you can work through it with me. So we are going to take the limit as h approaches 0 of x plus h to the third power minus x to the third power over h. Now, if you remember your Pascal's triangle, then you will remember the coefficients to deal with this cubic. If I'm saying Pascal's triangle and you have no idea what I'm talking about, then possibly off to the side what you're going to need to do is multiply x plus h times x plus h times x plus h in order to expand this piece right here. I'm just going to expand it using Pascal's triangle. So that's going to give me x to the third plus 3x squared h plus 3xh squared plus h to the third, minus the x to the third that was already in the numerator all over h. And now I know that x to the third and negative x to the third is 0. Everything else is going to stay. So the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed all over h. And they all have an h in common, so I can divide the h out. 3x squared plus 3xh plus h squared. And now I can take the limit as h approaches 0. As h approaches 0, this is going to 0 and this is going to 0. So this limit is going to be 3x squared. So I can say that f prime of x is equal to 3x to the second power. Now I encourage you to pause the video and try to work through number 5 on your own, remembering you may need to do some common denominator work to get you through it the rest of the way. So here we have the limit as h approaches 0 of 1 over x plus h minus 1 over x, and that whole quantity is over h. So I'm going to rewrite that, and I'm actually going to rewrite, instead of writing it all over h, I'm going to rewrite it as 1 over h in the front. So 1 over x plus h minus 1 over x. Now, in order for me to do any work here, I'm going to need a common denominator, and that common denominator is going to be x times x plus h. So I'm going to multiply the first part by x and the second part by x plus h in the form of 1. So this is going to give me x times x plus h in the denominator for both of them. That was the point, right, to get my common denominator. Here I'm going to have 1 times x is x. Here I'm going to have minus x plus h. And now if I combine like terms to make this one fraction, it's x minus h. So that's going to be just negative h. So I'm going to have the limit as h approaches 0 of 1 over h times that common denominator, x times x plus h. So these h's are going to divide out. That's going to leave me with the limit as h approaches infinity of negative 1 over x times x plus h. And if I substitute in 0 for h to evaluate this limit, I'm going to get negative 1 over x times x plus 0, or negative 1 over x squared. So f prime of x is going to equal negative 1 over x squared. So we're going to extend this idea a little further to find the equation of a tangent line, because what two things do we need in order to write the equation of a line? We need a slope and a point. We just determined how to find the slope. And if we were given a particular x value, we could also use that to find the point and the slope at that particular point. So, first thing we're going to do is we're going to work through that limit process again. So pause the video and work through it on your own, and then unpause the video and see how you did. So here I have worked through that limit process. So go ahead and pause the video to check over your work. But we should get that the limit is going to end up being 2x, so our derivative is 2x. Now we're being asked to find the equation of the line that passes through this point, which means I want to know what is this derivative when x is 4, because x is 4 in that point, and that derivative would be 8. The derivative is the slope, so I just did all of this work to figure out what my slope of my tangent line is. I have a slope, I have a point, and I'm going to write it in point slope form. Y minus 13 equals my slope 8 times x minus 4. And then I'm going to have my tangent line. Now on number 7, it says parallel to the given line, and then it gives us our function. So go ahead and find the derivative of that function first, and then unpause the video and see how you did. So this is a lot like one of the examples that we did earlier in this lesson. Number 2, in fact, if you want to go watch me walk through that again. And what we need to do is we need to figure out when the derivative, so here's our derivative, 1 over 2 root x. We need to figure out when it is parallel to this line. Well, this line has a slope of 1/4, so we need to figure out when that derivative is the same, when the slopes are the same. Parallel lines have the same slope. Well, this is going to be the same if 4 is equal to 2 times the square root of x, or if 2 is equal to the square root of x, and if I square both sides, I'm going to get that x just needs to be 4. X needs to be 4. So now, if x is 4, I need two things to write the equation of a line. I need a slope, which I have. This is my slope, and I need a point. If x is 4, then f of 4 would give me the other part of the point that I need. 4, if I plug 4 into here, the square root of 4 is 2. So y minus 2 equals 1/4 times x minus 4 would be the equation of that parallel line. So now we have extended this idea of slopes of tangent lines to writing the equation of that particular tangent line. So recapping what we covered in this video. Chapter 1 talked a bit about the difference quotient and how to use the difference quotient to find the slope of the secant line. We're extending that idea to say, what if we want the equation of the tangent line to our curve? And that leads us to the idea of taking the limit of that difference quotient, which is the derivative. The slope of the tangent line is the derivative. We then did a lot of practice where we actually found the slope of the tangent line and we used appropriate notation and learned what that notation was at a particular point. And then we also explored some problems where our final answer gave us the function. And then we tied those two ideas together and extending it to writing the equation of a line, since we can evaluate our derivative at a particular value to find the slope at that value, and then rewrite the equation of a line. So go ahead and write down any questions you have, post them below, or let me know, and I look forward to supporting you on this. Thanks for listening.